Hello, my name is Alexander Parmelo. I'll be doing an oral presentation for Nuclear Energy Engineering Technology Capstone, nuc495, January 2018 at Thomas Edison State University. The topic is Fukushima Daiichi Nuclear Accident Review and Response. The outline of the topics covered here will be plant design, what happened, sequence of events, radiological releases, and impact on the United States nuclear fleet. Plant design. The Fukushima site consisted of 6 reactors, generating almost 5,000 megawatts electric. Unit 1 was a GE Mark I boiling water reactor, generating 460 megawatts, in operation since 1971. Units 2 through 5 were GE Mark I BWRs, generating 784 megawatts, in operation since 1974. Unit 6 was a GE Mark II BWR, generating 1,100 megawatts, in operation since 1979. Fukushima reactors. Status of the units prior to the event. Unit 1 was in operation at rated power with all safety systems and both emergency diesel generators operable. High pressure coolant injection and isolation condensers were available and in standby. Reactor water level and pressure were normal for power operations. Unit 1 had been in operation since September 27, 2010. Unit 2 was in operation at rated power with all safety systems and both emergency diesel generators operable. High pressure coolant injection and reactor core isolation cooling were available and in standby. Reactor water level and pressure were normal for power operations. Unit 2 had been in operation since November 18, 2010. Unit 3 was in operation at rated power with all safety systems and both emergency diesel generators operable. High pressure coolant injection and reactor core isolation coolers were available in standby. Reactor water level and pressure were normal for power operation. The startup transformer was out of service for planned modification work. Unit 3 had been in operation since September 23, 2010. Unit 4 was shut down and had been in an outage since November 30, 2010. All fuel was in the spent fuel pool to facilitate reactor pressure vessel shroud work. The cavity gate was installed, isolating the spent fuel pool from the upper pools. The 4 Alpha emergency diesel generator was out of service for planned maintenance, with the 4 Bravo emergency generator operable and standby. Unit 5 was in a refueling outage since January 3, 2011. The reactor was recently refueled and reassembled. In preparation for leak testing, residual heat removal was secured earlier in the morning. Both emergency diesel generators were operable. Unit 6 was shut down in a refueling outage since August 14, 2010. The reactor was refueled and reassembled. RHR Bravo was in service. All emergency diesel generators and safety systems were operable. Here we see the simplified drawing of a boiling water reactor. It uses demineralized water as coolant and neutron moderator. Heat is produced by nuclear fission in the reactor core, and this causes the cooling water to boil, producing steam. The steam is directly used to drive a turbine, after which it is cooled in the condenser and converted back to liquid water. This water is then returned to the reactor core, completing the loop. The cooling water is maintained at about 1000 psig, so that it boils in the core at about 550 degrees Fahrenheit. This is a typical BWR fuel assembly. GE Mark 1 and 2s require 700 to 800 of these assemblies to make up a core. BWR overview. Here you can see the general layout of a Mark 1 BWR. Containment building with suppression pool, concrete shield plug, with the fuel storage pool near the top of the reactor. Unit 1's emergency core cooling system was made up of isolation condensers. They draw steam from the reactor, pass it through a heat exchanger, and return the condensate back to the reactor. However, alternating current is required to fill up the heat exchanger. Without water addition to the coolant side, it only has 2 to 6 hours of cooling capacity. Unit 2 and 3 rely upon reactor core isolation cooling. This system employs a steam-driven turbine pump that can add water to the core. However, it requires DC as well as AC current for control, and it will only last as long as suppression pool temperature allows. This slide illustrates the idea of decay heat. Although units 1, 2, and 3 were all operated at 100% power prior to the earthquake, seismic monitors scrammed all 3 plants as soon as the earthquake was detected, allowing the plants in a relatively undamaged way to cool down for almost 1 hour. That reduced the decay heat from 7% to 2%, greatly enhancing the ability to respond to the accident. This slide illustrates different temperatures which affect material composition of the core. You can see as at a temperature of as little as 1000 degrees centigrade, ballooning and bursting of fuel rod claddings, releasing volatile fission products can happen. At temperatures close to 2000 degrees centigrade, the zircali water reaction starts releasing hydrogen in flammable quantities. And melting of uranium dioxide happens at 2800 degrees centigrade. Station staff. Operations staffing at the time of the event. The operating crews consisted of the following. Units 1 and 2 had 11 operators and 1 trainee. Units 3 and 4 had 8 operators and 1 trainee. The normal operating shift organization for each of the 2 unit crews includes 1 shift supervisor, 1 assistant shift supervisor, 2 senior operators, 1 assistant senior operator, 2 main shift operators, and 4 auxiliary operators. Station staffing at the time of the event: 400 people, about 130 operators, and 270 maintenance personnel were available for the recovery process. About 70 TEPCO employees and about 40 people affiliated companies were engaged in initial field work to recover units 1 through 3. Most of the work was recovery of instrumentation and power supplies. What happened? On March 11, 2011 at 2:46 p.m., the 4th largest recorded earthquake with a magnitude of 9.0 on the Richter scale hit. The operating units responded well, with all safety systems being operational and the diesel generators loading. Units 1, 2, and 3 were subcritical within 15 minutes. Although the units responded well to the initial earthquake, the danger was yet to come. In about an hour, a tsunami well above design basis would arrive, taking with it all available off-site power as well as emergency diesel generator power. Without this power, operators would have little instrumentation or means of controlling the core. This slide illustrates Fukushima Unit 1's design basis. As we can see, this particular tsunami exceeded design basis by at least a factor of 2. Losing off-site power might have been foreseeable in such an accident, since the majority of the components are not safety related. However, losing emergency diesel generator power, which made most of the instrumentation of the core and ability to vent and add water to the core, would lead the station on a path of peril. Sequence of events. As discussed, the earthquake removed all off-site power. The tsunami removed all emergency diesel generator power after an hour. All that remained was the uninterruptible power source batteries, which would last 8 hours. When those batteries were exhausted, there was no power remaining to operate valves or instrumentation. The following slides will discuss the event in greater detail. You can see the earthquake happened, the plants initially scrammed, but there's still decay heat products. Containment isolates, closing off all non-safety related penetrations of containment. Cuts off the machine hall, and if containment isolation succeeds, a large early release of fission products is highly unlikely. The diesel generators start, and emergency core cooling systems are supplied. Plant is in a stable state. About an hour after earthquake, the tsunami hits the plant above the design basis, flooding the diesel generators and essential service water building, causing a station blackout. Only the batteries are still available, and there's a failure of all but one emergency core cooling systems. Initially, the isolation condenser for Unit 1, which uses the condensate storage tank water as a heat sink, was used to remove the decay heat from the shut-down reactor. After about 2 hours, the 26,000 gallons of water in the isolation condenser is boiling. The CST water is not available, and no heat removal other than IC boiling was available for Unit 1. Boiling began in the suppressor pool, and the dry well pressure began to increase about 11 hours after the station blackout. In about 16 hours, the water level in the core began to decrease, and core degradation occurred. Venting occurred at about 23 hours after the station blackout, and hydrogen explosion occurred in the reactor building about 1 hour after that. Seawater was injected into the core at about 31 hours after station blackout. Unit 2. The reactor core isolation cooling system, which operates on steam from the reactor and uses makeup water from the wet well or CST, operated for 66 hours. High pressure coolant injection wasn't used or didn't work for Unit 2. DC power from batteries and the use of DC powered pumps were lost after 70 hours. Although seawater was injected within an hour after the loss of RCIC, it appears that water level continued to decrease in the reactor vessel, and dry well pressure increased. Significant pressure increases were observed in the reactor vessel. Dry well pressure stayed high on March 15th, and an explosion was heard in the lower part of the reactor building. It is believed that the primary containment was damaged. Chorus, Unit 2. Hydrogen burn inside the reactor building, probably damage to the condensation chamber, uncontrolled release of gas from the containment, release of fission products, temporal evacuation of the plant, high local dose rates on the plant. Wreckage hinder further recovery work. No clear information on why 2 behaved differently. Unit 3. On March 12th, reactor core isolation cooling shuts down unexpectedly and cannot be restarted. The operators attempt to restart RCIC, but as soon as the steam stop valve is opened, it would reclose. After an hour of losing RCIC, high-pressure coolant injection automatically started on a low reactor water level signal and began to restore reactor water level. In preparation for transitioning injection to the diesel-driven fire pump, the operators secured the high-pressure coolant injection system and would use safety relief valves to control pressure. When operators attempted to open a safety relief valve, it failed to open. With high-pressure coolant injection isolated and no safety relief valves open, reactor pressure quickly increased, well above the discharge pressure of the fire pump, preventing water injection. Operators unsuccessfully attempted to restart high-pressure coolant injection and were unable to restart RCIC locally. They next attempted to inject water by diesel-driven fire pump, but the reactor pressure was way too high. Injection into the reactor was lost, and at approximately 4:15 in the morning on March 13th, the reactor core started to uncover. A large hydrogen explosion occurred in the Unit 3 reactor building at 11:01 on March 14th. The explosion destroyed the secondary containment and injured 11 workers. The large amount of flying debris from the explosion damaged multiple portable generators and temporary power supply cables. Also disabled some fire trucks that were going to be used for water injection on Unit 2. Off-site power was restored to Unit 3 on March 22, 11 days after the event. On March 15th, a hydrogen explosion occurred in the Unit 4 reactor building. This was unexpected, as workers did not believe there was enough decay heat in the pool to result in overheating. Water level in the Unit 4 spent fuel pool never dropped below top of fuel. The most widely accepted theory is that vent gases from Unit 3 backflowed into Unit 4's building during venting. This is a combined summary of the events after the earthquake. This again is a summary of events after the earthquake. Notice how quickly Unit 1 encountered core melt, and Unit 3's hydrogen explosion affected Unit 2 and Unit 4. This is an aerial photograph of the site at the time of the event. Operators were using visible steam plumes to determine if there was still water in the cores. Radiological release. Directly on the plant site, before the explosion in Unit 2, the dose rates were less than 2 millisieverts per hour, mainly due to released radioactive noble gases. After the explosion in Unit 2, there were temporary peaks of up to 12 millisieverts per hour. There was also local peak values of up to 400 millisieverts per hour. Currently, the dose rate is 5 millisieverts per hour. These dose rates limited the time workers had in the field to work. Release of fission products during the meltdown. Xenon, cesium, and iodines were the major constituents. Uranium, plutonium remain in the core. Fission products condense into airborne aerosols. They discharge through valves into water of condensation chamber. The pool scrubs a major fraction of the aerosols. Xenon and remaining aerosols enter the dry well, where they deposit on the surfaces to further decontaminate the air. Containment is the last barrier between fission products and the environment. The wall thickness was 3 centimeters. Design pressure was 4 to 5 bar. Actual pressure got up to 8 bars. There are both positive and negative effects of depressurizing containment. The positive effects are to reduce the pressure in containment to below design basis and allow water injection. The negatives are releasing a small amount of aerosols, which include iodine and cesium, the release of all noble gases, and a release of hydrogen, which really could be good and bad. You don't want the hydrogen in containment to explode, but it releases hydrogen into the service floor where it can explode there. Now we'll look at the spent fuel pools, which also lost all cooling capabilities. Due to maintenance, in Unit 4 the entire fresh core was stored in the pool. Time of the dry out of the pools, Unit 4 would take only 10 days due to its freshness. Units 1, 2, 3, 5, and 6 would take a few weeks. It was unknown at the time whether the pools were damaged due to the earthquake. The consequences of a spent fuel pool uncovery would result in large release because there's no suppression pool to absorb some of the fission products. On March 12th, operators entered Unit 1 reactor building in an attempt to vent containment. The reactor building had elevated dose rates and a steam-filled environment. The operators wore firefighting turnout gear and self-contained breathing apparatus. They were provided with electronic dosimeters set to alarm at 10,000 millirem and potassium iodide for thyroid protection. The first team opened a valve on the second floor of the reactor building, but elevated dose rates in the torus room required the second team to turn back before completing its mission. One of the operators received a dose of 10,630 millirem while in the torus room. This was reported to authorities as an overexposure because it was above the 10,000 millirem exposure limit. Operators in Unit 3-4 control room were directed to wear charcoal respirators after the Unit 1 explosion. To continuously staff their posts required periodic removal of their respiratory protection. A few of the operators wore conventional eyeglasses, which prevented their respirators from sealing properly. As a result, 2 operators in the Unit 3-4 control room received doses in excess of the initial 10,000 millirem, and later the 25,000 millirem emergency dose limit. One received 67,000 millirem, of which 59,000 millirem was internal. The other received 64,000 millirem, with a total internal dose of 54,000. On March 13th, operators in the Unit 3 and 4 control room had to move to the Unit 4 side because dose rates on Unit 3 side had reached 1,200 millirem per hour. The TEPCO medical chief directed site personnel under 40 years of age to take potassium iodide, while older workers were given the option. This is an aerial photograph with dose rates overlaid. You can notice several dose rates are in excess of 10,000 millirem per hour. Impact on United States reactors. In 2008, the NRC established the Bravo 5 Bravo requirements to defend against beyond severe accidents. It requires the procurement of high-pressure portable equipment designed to enable core cooling with the loss of all off-site as well as on-site backup power. It also establishes memorandums of understanding with local fire stations to establish the plant as a priority in the area. Unfortunately, these requirements were considered top secret and were not adequately conveyed to the Japanese nuclear fleet. Bravo 5 Bravo requirements include a review of all external events, including fire, flooding, explosion, earthquakes, to ensure that there is a backup emergency equipment that can support a station blackout. Further, should review training for extreme station blackout events and procedures. Ensure that emergency batteries are qualified for worst-case events for flood, fire, explosions, and that there is portable high-pressure pumps and associated equipment that is required for core cooling. Lessons learned. Prepare for the unexpected. When periodic reviews or new information indicates the potential for conditions that could significantly reduce safety margins or exceed current design assumptions, a timely, formal, and comprehensive assessment of the potential for substantial consequences should be conducted. An independent, cross-functional safety review with a plant walkdown should also be conducted to fully understand the nuclear safety implications. If the consequences could include common mode failures of important safety systems, compensatory actions or countermeasures must be established without delay. Core cooling. Ensure that, as the highest priority, core cooling status is clearly understood and that changes are controlled to ensure continuity of the core cooling is maintained. If core cooling is uncertain, direct and timely action should be taken to establish conditions such that the core cooling can be ensured. Containment venting. Emergency and accident procedures should provide guidance to vent containment to maintain integrity, purge hydrogen, and support injection with low pressure systems. Procedures should also provide guidance for performing venting under conditions such as loss of power and high radiation levels, and high temperatures in areas where vent valves are located. Accident response. Nuclear operators must establish the necessary infrastructure to respond effectively to severe accident conditions, mitigate core damage, and stabilize the units if core damage does occur. This infrastructure includes necessary personnel, equipment, training, and supporting procedures to respond to events that may affect multiple units, last for extended periods, and be initiated by beyond design basis events. Provisions should also be made to allow an effective corporate and industry response in support of the effective nuclear operating organization. Staffing. Establish strategies for staffing operating crews, other key plant positions, and site and corporate emergency response organizations quickly in the initial stages of a multi-unit event and over the long duration of the event response. Human limitations. Establish contingency plans, training, and guidance to help personnel cope with the emotional concerns that can impact decision-making and reduce personnel effectiveness during a natural disaster or nuclear accident. Emergency preparedness. Ensure primary and alternative methods for monitoring critical plant parameters and emergency response functions are available. Use drills and exercises to ensure emergency response personnel are able to use the available monitoring tools and methods. Ensure those who possess the expertise to operate specialized accident response equipment are available and are prepared to respond to a severe accident. This may be accomplished by training and qualifying members of the station emergency response staff to perform these functions. Roles and responsibilities. Clearly define and communicate the roles and responsibilities of emergency response personnel to help ensure effective post-accident communications and decision-making. Design and equipment. Equipment required to respond to a long-term loss of all AC and DC power and a loss of the ultimate heat sink should be conveniently staged, protected, and maintained such that it is always ready for use if needed. Procedures. Conditions during and following a natural disaster or an internal plant event may significantly impede and delay the ability to respond and take needed actions. The potential for such delays should be considered when procedures and plans for time-sensitive operator actions are being established. Knowledge and skills. On-shift personnel and on- and off-site emergency responders need to have in-depth accident management knowledge and skills to respond to severe accidents effectively. Operating experience. Actively participate and make best use of operating experience information shared in international organizations and forums. When considering the applicability of significant operating experience from international events, go beyond the event causes and transient initiators and consider the potential to experience the same consequences through other means. Take timely action to strengthen defenses to such vulnerabilities. Nuclear safety culture. Behaviors prior to and during the Fukushima Daiichi event revealed the need to strengthen several aspects of nuclear safety culture. It would be beneficial for all nuclear operating organizations to examine their own practices and behaviors in the light of this event and use case studies or other approaches to heighten awareness of safety culture principles and attributes. In addition to the Bravo 5 Bravo requirements, the Nuclear Energy Institute Recommendation 12-06 institutes requirements for flex equipment, which provide a diverse and flexible means to prevent fuel damage while maintaining containment function in beyond design basis external event conditions, resulting in extended loss of AC power and loss of normal access to the ultimate heat sink. The objective was to establish an essentially indefinite coping capability by relying upon installed equipment, on-site portable equipment, and pre-staged off-site resources. The foundation of the FLEX program is to maintain core cooling, containment integrity, and spent fuel pool cooling. Both plant and flex equipment that provides means of obtaining power and water to maintain or restore key safety functions for all reactors at a site. This could include equipment such as pumps, generators, batteries, battery chargers, compressors, hoses, couplings, tools, debris clearing equipment, temporary flood protection equipment, and other supporting equipment or tools. Reasonable staging and protection of flex equipment from beyond design basis external events applicable to a site. The flex equipment would be reasonably protected from applicable site-specific severe external events to provide reasonable assurance that a number of sets of flex equipment will remain deployable following such an event. Procedures and guidance to implement flex strategies. Flex support guidelines, to the extent possible, will provide pre-planned flex strategies for accomplishing specific tasks in support of emergency operating procedures and abnormal operating procedures functions to improve the capability to cope with beyond design basis external events. Programmatic controls that assure the continued viability and reliability of the flex strategies. These controls would establish standards for quality, maintenance, testing of flex equipment, configuration management, and periodic training of personnel. Plant-specific analysis will determine the duration of each phase. Recovery of the damaged plant is beyond the scope of flex capabilities, as the specific actions and capabilities will be a function of the specific condition of the plant, and these conditions cannot be known in advance. To the extent practical, generic thermal hydraulic analysis will be developed to support plant-specific decision-making. Justification for the duration of each phase will address the on-site availability of equipment, the resources necessary to deploy the equipment consistent with the required timeline, anticipated site procedures following the design basis external event, and the ability of the local infrastructure to enable delivery of equipment and resources from off-site. Flex strategies. Flex employs a three-phase approach. Phase 1. Initially cope by relying on installed plant equipment. Phase 2. Transition from installed plant equipment to on-site flex equipment. And Phase 3. Obtain additional capability and redundancy from outside equipment until power, water, and coolant injection systems are restored or commissioned. Diverse and flexible to enable deployment of the strategies for a range of initiating events and plant conditions. Flex Phase 3 is comprised of a strategic alliance for flex emergency response. The SAFER system is an alliance established between AREVA and the Pooled Inventory Management System. The SAFER team is contracted by the nuclear industry to establish and operate the National SAFER Response Centers to purchase, store, maintain, and deliver emergency response equipment in the case of a major nuclear accident or beyond design basis external event in the United States. An effective response is dependent on integrated planning and response actions among the nuclear station, SAFER team, governmental authorities, and industry and vendor support personnel. There are two national SAFER response centers, one located in Phoenix, Arizona, the other Memphis, Tennessee. There are two SAFER control centers, one located in Birmingham, Alabama, the other one located in Lynchburg, Virginia.